Loving here from the University of Illinois. I'm going to talk about least dilatations of pure surface braids.
Thank you for giving me the opportunity to speak here and for showing up to listen to my talk. So I'd like to start by unpacking my title a bit. And so, of course, the first thing that I should establish, if I'm going to talk about the least dilatations of pure surface braids, is what are pure surface braids? So I'm going to, so I'll start with just this definition. So let's set some scenery, I guess. Throughout the talk, I'll let S sub Gn be a connected, oriented surface of genus G. And we're going to be looking at surfaces of genus with at least genus 2 and n greater than or equal to 1 punctures. And then just for convenience sake, I'll let S sub G denote the surface of genus G with 0 punctures. And so this brings us to our first definition, which is the definition of the pure surface braid group. So the n-stranded pure surface, I'll call it the n-stranded pure braid group of a genus G surface which I'm going to denote by P B sub n of SG. I can define this to be the fundamental group of the configuration space of m points on a surface. And so what I mean by this is I mean distinct ordered n tuples of points in S. So this would be a subspace of like the nth Cartesian product of S. And so this is kind of very, if you know, like have thought about braids at all, this is reminiscent of kind of the classical setting for the pure braid group, which is typically just denoted PB sub n, which is just defined to be the fundamental group of the configuration space of m points in the complex plane. So this is kind of familiar, and it's a very natural extension of this classical case. But I like to think about mapping class groups, and I like to talk about mapping class group things. And so I want to give a slightly different definition, and it's going to be the way I think about them. But first, let's just recall a couple of things. So I'm just going to quickly write down my notation. This is going to be my notation for the mapping class group. And this is just the group of orientation preserving homeomorphisms of my surface up to isotopy, or if you're unfamiliar, up to homotopy. And when I'm looking at the homeomorphisms of my punctured surface, I'm going to require that they preserve the set of punctures setwise. And then I can think of a subgroup of the mapping class group, which I'll call the pure mapping class group. So this sits inside the full mapping class group. And this will simply be the mapping classes which fix each puncture. And so these are the two things that I'm going to need to give my second definition for the pure braid group. So let's consider the following short exact sequence. So this is the only exact sequence I'm going to write down, so don't worry, this is not going to get all algebraic or something. So let's consider the short exact sequence given as follows. So we're going to send 1 into the kernel. So I'll describe what this map script f is. And it's going to be the kernel of a map between the pure mapping class group into the mapping class group of the closed surface. So this is our map script f, where this f is the forgetful map. And so what do I mean by that? I mean that we're just forgetting that we have these mock points or punctures on our surface, and we look at the mapping classes that they induce on our closed surface. So you could also think of it as like filling in the punctures. And so then what does this kernel look like? This kernel is simply the pure mapping classes which are isotopic to identity on the closed surface. And so this brings me to my second definition. So definition, I can now define the pure braid group to be the kernel, this kernel of script f, of this forgetful map. And so it's not immediately obvious that these are equivalent definitions, but it's a theorem of Berman from 1969. And she proved that, indeed, the pi1 of this configuration space is isomorphic to the kernel of this forgetful map. For, again, this is when g is greater than or equal to 2. OK, so this gives us a nice way to think about our pure braids as mapping classes. And now we can talk about mapping class group things. And so, as probably is given away by my title, the mapping class group thing I want to talk about is this thing called the least dilatation. Oh, but first, I guess one thing that maybe I wanted to draw a picture of just to get a feel for it. So I already said it out loud, that we can now think of these pure braids as being the pure mapping classes that are isotopic to the surface, to the identity on the closed surface. But then what would they look like in some sense? So I'll just try and draw a very maybe helpful picture, maybe not. But just to give you an idea of something maybe that will help later on when I'm talking about these, is that what you can actually think of these doing then is you could think of these pure mapping classes as acting on our surface by point pushing our mark points along closed curves that are based at those points. And so this gives us a kind of nice description, which we'll leverage later. And you can also note then that if we would have something like this, where we have some set of filling curves that we point push along, then since we're kind of mixing up every portion of our surface, maybe we get some nice dynamical properties, which now I'm about to talk about, which is something called pseudo-Anosovs. So let's go ahead and write that here. Does anyone have any questions at this point? No? OK. So we've talked a little bit about our pure surface braids. Now let's talk about the least dilatation. So Thurston gave a classification for the mapping class group into 3 types of elements: finite order, reducible, and pseudo-Anosov. I don't want to talk about the first 2, and I'm only really going to talk about this third one in a way that's important to me. So let me just not exactly say what a pseudo-Anosov is, but say kind of a nice property, which I guess does characterize. So pseudo-Anosovs are nice because they have nice dynamics, and we can talk about the way that they act on our surface in a really nice way. So a pseudo-Anosov mapping class F, so I'm going to write down something that's a bit hand-wavy, but then I'll draw a picture, which hopefully will illustrate what I mean. So I'm going to say it acts on S by stretching and squeezing, by a factor which I'll call lambda of f, which is a real number and it's greater than 1. And so what I mean by that it acts by stretching and squeezing, so we can think of on our surface of these like unstable and stable foliations which fill up our surface and which locally are going to look away from singularities. We'll get just nice kind of transverse foliations here. And if they're going to get squeezed and then stretched in the opposite direction, or if we have some singularity, we'll have them kind of crashing together like this. But still, we'll have a really nice action of the pseudo-Anosov, where we're going to kind of compress in one direction and squeeze out in the other. And so this stretching factor, lambda f, is what I'm going to call the dilatation. So it's also often called the stretch factor, which I guess makes a bit more sense. So this is the dilatation of f. And the thing that I'm going to study is something called the least dilatation, which lives up to its name as it's basically just, if we look at all pseudo-Anosovs in some subgroup of the mapping class group, we can say, well, how small can this stretch factor be? But I'm going to write it down because that's not quite true, because what I'm actually thinking of, so this is how I'm going to denote the least dilatation. So the least dilatation. What I'm actually mean is I'm going to look at the infima of not just the dilatation, but the log of the dilatation. And so I'll look at this over all of my mapping classes in my pure braid group, which are pseudo-Anosov. Oops. And so you can note that then I can use the same notation for the mapping class group, right? If I just look at all pseudo-Anosov in the mapping class group or any other subgroup. Okay, so we've kind of unpacked our title. Now we know what the least dilatation is. We know what our object of study is. So I think I'm ready to say what I proved about this. So I'll go ahead and write that here. So, theorem. It's a little bit notational because I am bounding some real number, right? But hopefully I'll unpack what the implications of this are a little bit. So one thing to know is that we have upper and lower bounds, which are both depend on the genus and number of punctures. And we also have that for, especially in the upper bound case, if we have enough punctures, right, we're going to get some constant upper bound for fixed genus. And then we also have that if we fix the number of punctures, so I'll write this down because it's kind of important. So if we fix n, we have then that this least dilatation is going to go to infinity with the genus. So this is interesting, and this will be more interesting once I put it into a little bit of context. So I am not the first person to study, as most grad students are not the first to study many things, to study this least dilatation. And one of the first results about it is due to Penner, and he studied the least dilatation of the full mapping class group. Oops. So theorem Penner in 1991. He showed the following bounds on the least dilatation of the mapping class group of a closed surface. And just to note, like these bounds, there's much better bounds than this now. They've been improved many times by many different people, but I'll just write down Penner's original bounds. And the thing to know about this, right, is that here we have a very different behavior. We have these kind of constants over G on both the upper and lower bounds. And so in particular, we have then that if we look at the least dilatation as G goes to infinity, we have that the least dilatation goes to 0. So we have these kind of very disparate behavior that's happening. Okay. But this is for a closed surface. What about for a punctured surface? So for a punctured surface, there's a kind of version of this type of theorem by Tsai from 2009. So let me go ahead and write that down. And what she showed is that for any fixed G, of course greater than or equal to 2, there is a constant, which I'll just denote C sub G. So this is just to denote that's relying on G, greater than 1, such that we have the following bounds on the least dilatation of the punctured surface. So we have this log n over this constant times n, and least dilatation of a punctured surface, and then G log n. And so here we have a kind of different behavior, but similar at the same time. What we have is that now for fixed n, for fixed G, we have that this least dilatation is going to, again, go to 0. So we see that the tendency is somehow that if you have enough room, if you are looking at a big enough subgroup, namely the whole group, you get this kind of, that you can get arbitrarily close to 0. OK, so what else did I want to point out? Oh, I just wanted to mention that these bounds that she originally proved had exponential dependence on G. And recently, Mahidi Yazdi proved this past year that you can get constants with polynomial dependence on G. OK. So minimal dilatation in the mapping class group has been studied, and it also has been studied in subgroups. So I just want to mention some names. I'm not going to write most of them down. But for instance, Farbleiner and Margalit studied the least dilatation in subgroups such as the Tweley group, the Johnson-Cornell congruent subgroups. Hirose and Kim studied them in hyperelliptic handle body groups. And then lastly, I will write this down. Where should I write it down? I'll write it down better. Spencer Dowdall, who some of you may remember, proved in his thesis some bounds on the least dilatation in the point-pushing subgroup. And so, oh, this is where I can go back to my picture. So I mentioned that what's really happening, right, when we're acting on our surface by these pure surface braids is we're somehow point-pushing on Mach points around our surface by closed curves based at that Mach point. And so when we talk about just the point-pushing subgroup, essentially what we're saying is we're just going to have one Mach point now, and we'll point-push along a closed curve there. And so what do I actually mean by point-push? I mean the action is like you put your finger down on your surface, and you drag it along that curve. And when you come back, that kind of drag that you did is held in place by your puncture. OK. So what is the result of Spencer? So it's actually kind of a two-part result. It was originally due to Dowdall. And then the upper bound was improved by Aougab and Taylor. And so we have that. In this case, we see behavior similar to what I pointed out for the pure surface braid group of n strands. So we have that these upper and lower bounds are dependent on G. And so as G goes to infinity, these upper and lower bounds are going to also go to infinity. And so, yeah, so this is due to Dowdall, this upper bound, and this lower bound is due to Aougab and Taylor. OK, cool. So my main motivation, now that you can kind of see them written next to each other, was to kind of extend this result from just the one-strand braid group to the n-stranded braid group. OK. Yes, please.
Your constants in your theorem, do you actually compute them, or is it like they exist?
This is a good point, yes. So I wrote it down like this because they're pretty messy. But when I can actually write down the explicit constants for both upper and lower bounds.
And are they like quite different?
So they're different in the sense that this is a log of a log.
No, like the constants. Like how big is the spread like between them if I don't know.
They're pretty small. They're like 4. This one is a little bigger. This is like 1/40 has a constant. But they're very small constants, I guess. This one, the constant lower bound for the lower bound is very, very small. It's like 0.0155. This is kind of, I'm not going to touch on it, but it's due to kind of we have a nice action on homology for the pure braid group. And so this gives us a way to give a lower bound on dilatation and bound it away from 0. For the upper bound, it is pretty nice. It's just 4 log 6. Once we have like a sufficient number of punctures with relation to the genus, we can give a nice construction. Yeah, so this is a good thing to point out. So I'll actually go ahead. I think we're ready to talk a little bit about how I proved this. And so let me write down the explicit bounds for the upper bound, because that's the first thing we'll talk about. OK. So I'll just restate my theorem, but now with the explicit bound. So just for the upper bound, we have then that the least dilatation is bounded above by this 4 log 2g over n plus 4 log 6. And so, oh, I just erased. So if I still had Dowdall's and Sam's thing up here, you would see that this is very kind of reminiscent. And you'll see as we go through the construction why it kind of looks like this. So the most important tool in the proof of the upper bound is a construction for pseudo-Anosov mapping classes, which is due to Thurston. And so I'm going to spend a little bit of time talking about this. because it's kind of the heart of what's going on. So since we're bounding like the least dilatation, for the upper bound, it's going to be enough just to produce pseudo-Anosovs with fairly small dilatation, right? We just need to show that something is fairly small, bigger than the amp. So we're going to do that using this construction of Thurston. So Thurston's construction. Did anyone else have any questions about like the statement of my theorem or anything? So Thurston's construction is going to rely on building these pairs of filling multi-curves. So we'll have a multi-curve A, a multi-curve B. So what do I mean by this? I just mean these are going to be our simple closed curves, which are pairwise disjoint. These are pairwise disjoint here. And what I want for them is that, so I want that A union B fill S. So we want that these collections of alpha and beta curves fill our surface. And what do I mean by that? I mean that S minus these curves is just a collection of disks. Or another way of saying this would be that any curve which is not in this collection has non-zero geometric intersection with one of these curves. Okay, so once we have this nice collection of filling curves, I'm going to define a way to act on our surface by them. So many of you may be familiar, but I'm just going to draw a picture anyway with a Dane twist. So say, let's look at T alpha I, where our alpha I is just one of these. Let this be is a Dane twist. It's going to denote a Dane twist about alpha I, where what I mean by this Dane twist is if we just look at alpha I as being some simple closed curve in this annual region, and we look at some other curve that crosses through it, then Dane twisting about alpha I will send this pink curve kind of around like this. And so what we're doing by Dane twisting is we just kind of cut along that simple closed curve, twist our surface around, glue it back together. And so what we're going to be talking about is a Dane twist about these collections of curves. And so we'll just define it in the most natural way possible, where our Dane twist, which is also, I guess, usually called like a multi-twist, but I usually call it just a Dane twist, is just the product of the Dane twists about the individual curves. OK. So now let's state what Thurston said about these. So theorem, Thurston, he said that there is a real number, mu greater than 1, and a homomorphism, which I'll denote rho, from the subgroup of the mapping class group generated by these multi-twists into PSL2R, given in the following. So we send the Dane twist about A to just this 1, negative square root of mu 0, 1, and we send TB to 1 square root of mu 0, 1. And so I said that OK, so this is great. So we have this homomorphism, but what can we use it for? And the important part, the punchline, is that now if we take some f in this subgroup generated by these twists, then this is pseudo-Anosov if its image under the homomorphism is hyperbolic. And the dilatation of f is the largest sorry if this is really small, it's the largest eigenvalue of rho of f. So since we're just sending this into PSL2R, this is just a subgroup of SL2R. So when I'm saying that this image, right, the image of f, this is just going to be some matrix. When I'm saying it's hyperbolic, I just mean that the absolute value of its trace is greater than 2, right? So in particular, we can look at something specific, which is what I'm going to use it for, is to look at this mapping class, T sub A composed with T sub B inverse. And we get that this is pseudo-Anosov. And it's pseudo-Anosov because its image under this map, you get a matrix which has trace 2 plus mu, and mu is greater than 1. And in fact, we have then that the dilatation of this composition of twists is bounded above by mu plus 2, which is the trace of that matrix, where this is something that we can actually get our hands on. So where mu is the largest positive eigenvalue of a matrix in transpose, where I'll say exactly what n is, where n is given by, we can define the entry, the ijth entry of n to be the intersection between our alpha I curve and our beta j curve. And so you're seeing that somehow we get a bound on dilatation, which is going to depend on this matrix, but this matrix is just composed with all these intersection numbers. And so we can get a hold of our dilatation in terms of the curves that we originally are going to use to construct our pseudo-Anosov mapping class. So this is very nice, and this is going to make it possible to actually compute these in a reasonable way. In particular, if we could find some filling multi-curves which have really small pairwise intersections, so each of the alpha and beta I intersect each other with very small intersection, and we don't have one curve which intersects a bunch of other curves, then this is going to give us a pretty good chance of producing a pseudo-Anosov with a small dilatation. Okay, so I think the only other thing I wanted to mention was then through some linear algebra, which I don't want to say, we can actually bound this mu specifically by the max row sum. So I might get to this, to use this later, the max row sum of this n transpose matrix. So we're going to be closer to some sort of way to approximate this. OK, so this is fantastic. And this is the heart of the proof for the upper bound. And in fact, it's the heart of the proof of the upper bound that Aougab and Taylor did. And so I want to touch briefly on their construction as well. So what they say is that we can get a pair, there's a pair of filling curves alpha and beta, which fill SG1 and such that the Dane twist, this kind of Dane twist and inverse Dane twist, it lies inside the point pushing subgroup. And we have a really nice bound. We can use a result of Ivanov to get a really nice handle on how often these two curves actually intersect. So we can bound it above by this quadratic in G expression. So I want to know, I'm not going to construct for you how they do the filling curves, but I want to just mention because it gives us later on a nice geometric intuition of what's going on our surface. So what they're actually doing to construct, so I'll just do it on a torus because that's the only case I can really draw the picture very easily, is they take two filling curves, and what they're going to do is they're going to point push one along the other. So for instance, I can draw a picture of just one action on the point pushing. So if we were to point push the red curve along the blue curve just once, we just kind of, so here's our mark point, we just kind of drag it out and along, tracing out until we come back to where we started. And this kind of point pushing, if you do this 3 times, so you kept going, you go once, go again, go 3 times, then this red curve and the initial red curve that we had here that we originally point pushed, together they're going to fill our surface, and together they intersect with this bound. Well, it doesn't, this bound doesn't quite work for genus 1 and 2, but we also have a nice bound here. And so because of this nice bound at intersection, we get a nice bound on the dilatation of this map. And in fact, in the case of just the point pushing, it's really nice because the computations are very easy if we just have 2 filling curves. So in fact, we get that, oh, I should probably not red and pink. We get that the dilatation of this point pushing map is bounded above by just twice the intersection, which is just equal to, well, I should say is bounded above by just this. And so this is what gives us our upper bound on the log of the dilatation. So now if we just look at the log of lambda, we get that nice term just for log g plus 2 log 24. And so you can see now how this is kind of looking very similar to the upper bound that I have from my theorem. OK, so let's go ahead and talk about how I do the upper bound for my theorem. So I have a picture for this. Let's see if it works. So I'm just going to illustrate it for the genus 4 with 8 punctures. Let's hope it works. Will it work? Yes. OK, good. So in general, what I want is I want to be able to so do I still have, let me just write down again what the upper bound is, the explicit upper bound, so we can see how this kind of correlates to the construction we just did. So I have the upper bound for PBNSG of this (2g over n) plus this constant. And so for the genus, so in general, what I want to do is I want to break up my surface into these subsurfaces of, at most, genus 2g over n. And so in the case of a genus 4 surface with 8 punctures, I'm going to split it up into genus 1 surfaces. And what I'm going to do on each of these subsurfaces is I'm going to go ahead and fill it with this filling pair, which Aougab and Taylor give me. So I have these. Again, you see kind of this picture here. This is what happens if I keep point pushing again 2 more times. And so the reason I want to kind of draw this down explicitly is because it matters, this geometric thing, because it allows us to actually count our intersection, like how many curves there are kind of between this puncture and the outside of that subsurface. OK, so I go ahead and I fill up those subsurfaces, but I need something that fills my entire surface. And so I go ahead and add these red curves, which bound these twice punctured disks here, here, and here, here. And so now I have these red and blue curves together are going to fill my entire surface. And if you note that if we fill in these punctures, well, immediately these kind of bounding pair curves will become trivial. And then these ones, since all I did was act by point pushing, as soon as I fill in that puncture, this kind of just unravels, and these are isotopic to each other. And so since we're doing, that's why we have that twist and the inverse twist, because now once we fill in all the punctures, we're just going to have, we have these are trivial, these twists are all trivial, and then these ones are just going to be something that's isotopic to identity. OK. So in the case, so let me go ahead. So this is great. And we can now, since we've kind of written down what our multi-curves look like, we can go ahead and figure out what their dilatation is. So what I'm going to do to compute that is I'm going to draw a graph. So we're going to build bipartite graph, and we'll build it in like the most natural way, I think. So we'll go ahead and put a vertex for each of our curves. So I'll draw a blue vertex for each of our blue curves, and a pink one for each of our red curves. And then we put an edge between them if they intersect. And because of how nice our picture is, we actually know what the intersections between these curves will be. So in this case, this intersection, right, is 6, this is 8, this is 1. And these all look the same, right, just translated around. But in general, did I cover up again? In general, we have that nice bound on the intersection of the filling pair that Aougab and Taylor had. So they had the nice bound between their filling pair of this like 24g squared minus 24g plus 6 business. And so these are going to label these kind of high intersection edges. And then here, or this should be 2. We still just have 2 intersections because it's that curve, that puncture that's kind of out at the boundary of our filling curves. And so we can then compute it by, we can compute the maximum MOSUM by computing the weight of like all the paths of length 2 emanating from here. Okay, so this is the picture for this, but you see that the picture more or less will look the same. So we're always going to divide our subsurface up into these kind of cyclical subsurfaces, and then create those same filling curves on the Aougab-Taylor pair on the subsurfaces, and then those just twice, those curves bounding a twice punctured disk in between them. Okay. So I think this is all I wanted to say about this, so I'll go ahead and put the slides away. Does anyone have any questions? I guess I should have asked that before I put the picture away. Okay. So let's turn to the lower bound. Let me clear some board space. So the upper bound is really nice because it's so constructive. We're just constructing examples of nice pseudo-Anosov pure surface braids that have small dilatation. For the lower bound, it's maybe not quite as visual, but I think I can give some sense of what we're doing. So the lower bound. So let's just take some pseudo-Anosov pure braid. And what we're going to do is we're going to now take advantage of this thing that I've kind of mentioned a few times, right? That really the characterization of the pseudo-Anosov is that if we look at it on the closed surface, it's isotopic to identity. So if we can get some handle on what this isotopy is, it's going to give us some leverage. And so the way we're going to do that is through a result of Imayoshi, Ito, and Yamamoto. And what they do is they say that there is a canonical isotopy. And what I mean by canonical is that I mean it's independent of the choice of representative homeomorphism. It's a canonical isotopy through quasi-conformal maps. And so what we're going to be able to do, and what they give us a way to do, is to relate the dilatation of our pure braid with the quasi-conformal dilatation. So through quasi-conformal maps, so I should call my isotopy something. So let's call it f sub t. such that the log of the quasi-conformal dilatation of, so the K sub t will denote the quasi-conformal dilatation of F sub t, gives a lower bound for the log of the dilatation of my original pseudo-Anosov braid. And this is for each t. So now this gives us a way to actually get a handle on our exact isotopy. And so their result is actually, they only did it for the case of n equals 2. So if you try to find this, it's not anywhere, but their stuff carries through well for our situation also. And their bound is a little different, but you can improve it to this. So this is, if you look up their paper, this doesn't quite look like what they have, but it is. Okay. Okay, so now let me start to draw a picture. So what is my picture so far? My picture so far is that we took our pure braid, right? We have it acting on our surface. And now we're translating our picture to look at this isotopy. So I guess these aren't quite in the same place, right? Because F is acting on a punctured surface. This is isotopy on a closed surface. And so what we want to do now is we're going to lift it up. So we're going to lift Ft to the universal cover. And lift it to the hyperbolic plane. And we're going to apply a result of Teichmuller and Gehring. But I'm going to attribute it to Kra because his is the only decent citation you can find. And so what does he say? It says that, so I'm going to kind of put together a few things. Again, this is not quite what you'd find, but essentially what we can say is that now we can look at this action of this isotopy, which we lifted. So I should say that we are being a bit careful. We're picking a specific lift so that this is the identity on the circle at infinity. So that we get this lower bound on the quasi-conformal constant in terms of the distance that points are moved in the hyperbolic plane. So if we look at some point x and its image under the lift of our isotopy, we have now a way to give a lower bound. So we moved from relating the pseudo-Anosov dilatation to the quasi-conformal dilatation of the isotopy to now relating the quasi-conformal dilatation to this translation distance on the hyperbolic plane. But we want some lower bound, right? The thing I wrote down at the beginning is in terms of our surface, right? Is in terms of genus and the number of punctures. So we're going to send things back down by the covering map and look at what happens here. So we'll look at how the isotopy acts. And since this is distance decreasing covering, and in fact it's two Lipschitz because I didn't mention it here, but here we're using the point-away metric, and then we're sending it back down, and we're using the hyperbolic metric here. So we get that now, so I'll just state it. We have that the distance, right, between these 2 points on our surface give a lower bound on this distance, right, between the points from the lift of the isotopy. And so now we've related all the way from the pseudo-Anosov dilatation to translate somehow how far our pseudo-Anosov is translating points on our surface. Okay, which is almost enough, except to have this actually be a good lower bound, we need to know that when our surface is big and we have a lot of punctures, that this distance is actually increasing, right? That we don't just send points really close to each other. That's not going to really do that's not going to help us at all. And so I guess I shouldn't have erased it, but the picture that I'm thinking of is that one that I drew at the beginning, right? Where we had those curves that we can point push along. And notice that when we have this kind of family of filling curves and we point push along it, this is going to give us a pseudo-Anosov. And the amount that we kind of are traveling is related to the length of these curves, right? And so if you think of this filling curve as some graph embedded in our surface, if we can say that the diameter of this is big enough, then we can ensure that we somehow move our points far enough. And so that brings us to the last thing that I want to mention, which is a result of myself with Hugo Pollier, where we show that, in fact, if we have, so let gamma be an embedded graph in our surface such that, so when I say filling, it's the same thing that I meant with curves, such that if we subtract out our graph, we get a collection of disks. Then the diameter of gamma is bounded below by this, not very nice, but this term in terms of the genus. And so we're able to say that indeed we're moving points enough here. Okay, so I think that's all I wanted to say. So thank you very much.
Any questions for Marissa?
Can you say briefly maybe how the proof goes for this last thing?
How the proof goes for the last thing. So for this diameter, we embed our graph, and then we look at a triangulation of our graph given by Bucer. You can decompose your surface into things called trigons. So it's kind of like a normal triangulation, except when you have collars, instead of dividing that into trigons, you're going to put something called, to regular geodesic triangles, you're going to put something called trigons. So they're just kind of annular neighborhoods that look like, they just have kind of one closed geodesic loop and then just two geodesic arcs on the other sides. And so the advantage of using Bucer's triangulation is that he gives you a control on the size of your geodesic triangles. And so in particular, we can kind of translate this graph in terms of some sort of combinatorial length in a thing, and then we can translate that back to the hyperbolic distance because of the nice bounds he gives, the upper and lower bounds on the sides of our triangles. And that allows us to actually make a statement about the size of our graph.
Maybe this is silly, but when you're talking about bounds like this, the first thing I think is you could imagine deforming the surface so that
this is really, really
stretches.
long.
Yeah, and
Yes.
then you end up getting two surfaces, each with one puncture. Do you think that?
Oh, so we're not going to, if you're doing that, you would go all the way until you have a cusp or something, right?
Yeah.
So you can't deform it that far. We're taking nice surfaces. But in general, right, yeah, you could get this neck to be, this collar to be really long.
I was just wondering if it's maybe too silly to think of you could try and look at how these two results talk to each other at that point. I don't know if maybe the earlier result rules out cusps, as you're saying, but because you have something about how curves get moved around on punctures, and you have something about diameters of embedded graphs control again in terms of just genus punctures here.
Maybe.
But I think if you have really skinny necks, then you can, points are actually.
Yeah, but so the problem in our situation was if these are short somehow, right? If these collars are really short, then maybe points aren't actually getting pushed away that far from each other. The longer you get, the better it is for us, right? Points because since we're pseudo-Anosov, these curves that we push along have to fill our surface. So in particular, one of them would have to pass through that neck, right? So that's.
Any other questions? Before we thank Marissa again for an awesome talk, if you'd like to go to lunch, let's meet in the mailroom in 3 minutes.